We are opening our WFEO Side-event, Engineering Solutions for Water Adaptation. Distinguished speakers, dear colleagues, ladies and gentlemen, good morning, good afternoon, good evening to all of you, and welcome to this very interesting webinar on engineering solutions for water adaptation. This event is a side event organized by WFEO, the World Federation of Engineering Organizations, within the United Nations Science, Technology and Innovation Forum 2023 for Sustainable Developing Goals, that is taking place at the United Nations headquarters in New York yesterday and today, 3 and 4th March 2023. I am delighted as the president of WFEO to have this opportunity of opening this webinar and thank our distinguished speakers, Dr. Ignacio González-Castelao, Dr. João Paulo Lobo-Ferreira, Professor Innocent Nhapi, Dr. Qian Yu, Engineer Martin Manuhwa, and Dr. Chee Meng for their willingness to share their world-renowned expertise with us. Thank you very much. WFEO has committed itself to mobilize the global engineering community towards accelerating the delivery of the United Nations Sustainable Developments. Milestones in this strategy include key partnerships with UNESCO, especially the UNESCO first and second engineering reports published in 2011 and 2021, the WFEO UNESCO Paris Declaration on Advancing the United Nations SDGs through Engineering, and the proclamation of the UNESCO World Engineering Day for Sustainable Development that we celebrate each 4th of March from 2020. The daily work of WFEO is mainly conducted through our standing technical committees and policy implementing committees, which are required to focus on particular SDGs and report and publish on how those goals can be achieved through engineering or how engineers contribute to progress. Recognizing the importance and cross-cutting role of water with most of the United Nations SDGs and its decisive contribution to achieving the goals of the 2030 Agenda, WFEO established the Standing Technical Committee on Water in 2020 under the chairmanship of Ignacio González-Castelao and hosted by the Institute of Engineering of Spain and the Ordem dos Engenheiros of Portugal, these two national members of our federation. This aims to provide a strong platform to coordinate the engineering work around the world, and so WFEO will be able to make a significant contribution to accelerate the delivery of SDG 6. And here, I would like to congratulate Ignacio for holding this webinar that represents his active and effective commitment to building a recognized affirmation of WFEO in the discussion and search for solutions to this planetary issue. Global water problems, including droughts and floods, pollution caused by natural and anthropogenic-driven events, such as extreme rains, rising sea and river levels, bushfires, and untreated domestic and industrial effluents, are key challenges which require integrated water resources planning and management, considering surface and groundwater as a single interconnected resource. Water engineers can provide the necessary expertise and support to address these global challenges, applying scientific knowledge and innovative technical solutions. In 2020, 74% of the global population had access to safely management manage the drinking water services, up from 70% in 2015, and 54% of the global population had access to safely managed sanitation services, up from 47% in 2015. Today, some 2 billion people are living in countries experiencing high water stress, and innovative engineering solutions for access of water and sanitation are urgently needed. Adapting to climate changes is making the challenge even more difficult. Global institutions and governments must cooperate to accelerate the capacity building through STEM and encourage young people, especially girls, to become engineers and study hydrology to make a significant difference in improving the life quality of their community. Engineers are needed to design and operate dams and reservoirs, channels, pipelines, water treatment plants, and also for planning and managing water resources. We want to promote the emerging nature-based engineering solutions to improve the rivers, underground aquifers, and urban drainage management. We also want to accelerate the technological development for safe wastewater reuse, desalination, and new irrigation technologies for agriculture pressing needs. More engineers are also needed to contribute to disaster risk assessment and management, to help prepare for floods and droughts, to reduce economic losses from natural disasters. An important step in acknowledging the growing challenge of water scarcity is the launch of the Water Action Decade for 2018-2028 period, to mobilize actions that will help transform how we manage water. Engineers must deeply be involved in this process to turn words into action, strategy into effective projects, and the vision into field initiatives. The whole point here is mobilizing to leave no one behind. We hope that you help us to spread our vision and expectations, and I wish you a fruitful webinar. Well, this is my first words in this webinar, and now I will leave the floor to Ignacio González-Castelao, our chair of the WFEO Committee on Water. Ignacio, please, the floor is yours.
Thank you very much, José, for your kind words, and good afternoon, evening, or morning to all. I'm just going to make a very brief presentation. I'm going to make a very brief presentation or a general introduction about water adaptation. This term can be defined as the process of changing the way we do things to minimize negative impacts on our water resources in order to continue to exist or suit in a particular environment. The environment to which I refer is clear, and so far all our water resources are represented in those blue spheres, and the current status of these resources can be assessed through UN Water's monitoring progress on SDG 6 targets. Although there is a chronic and consistent lack of data on almost all water-related SDGs indicators, the average progress rate for all of them is 52%. This means that we need to accelerate action, as we are not yet moving at the speed and scale needed to achieve the sustainable development goals set for water. This current situation is exacerbated by primarily non-climatic factors such as population growth and current production and consumption patterns. Climate change is another problem to this current situation, increasing pressure to already stressed water resources. The scenario shown in this slide is the one that we must adapt to. Regarding climate change, the degree of mitigation we achieve will determine the level and measures needed for adaptation. The more mitigation, the less adaptation. The different climate scenarios expected simply indicate the speed at which we have to adapt. Some species will be able to tolerate this rate of adaptation, and others may not. Adaptation is not only constrained by physical limits, but also by the limits of governance, finances, and knowledge. In addition to scientific knowledge, it is necessary to recognize the value of other forms of knowledge, such as indigenous, local, or community science, to understand and evaluate adaptation process and actions. All these limits define the degree of adaptation that we can achieve, and beyond this degree, only partial or total forced migration remains. From an engineering perspective, we can group the main adaptation measures into three categories: those related to water supply demand, extreme weather events, and sea level rise. The third demand should be holistic and also refer to all other living beings and natural ecosystems. If we focus on adaptation measures related to water supply demand, we can say that climate change will affect water supply in terms of availability, quantity, and quality. Demand will be affected mainly by world population growth and the consumption patterns of current development model. The balance between a reduced supply and increased demand can only be achieved through adequate planning and integrated water resource management. But going further into integrated management, it should also be multisectoral, including soil and land management. 7 supply-side adaptation measures have been identified: improved knowledge, ecosystem and water bodies conservation or protection, water losses reduction, drainage, sewage and wastewater treatment, increased storage and regulation capacity, unconventional water resources, mainly desalination and reuse, and water transfers. Also, virtual water transfer is important here. 5 demand-side adaptation measures are proposed: improved knowledge or increased knowledge, awareness-raising campaigns on sustainable water use, increase the efficiency and effectiveness of water use in a sustainable manner, water losses reduction, and disruptive breakthroughs that promote lower water consumptions. This last measure is perhaps the most important because these advances make it possible to decouple development from water use and increase the planet's biocapacity. Regarding the adaptation measures for extreme weather events, I just want to highlight that catastrophes are increasingly seen by society as the public face of climate change. Climate extremes cause extreme events, but whether a meteorological phenomenon is catastrophic or not does not depend exclusively on the extreme events value taken by the climate element. Other factors, mostly caused by economic and social reasons, are the ones that can condition the catastrophic nature of an extreme phenomenon. Traditionally, these extreme events have been treated as an emergency or critical situations. These policies are changing worldwide, shifting from a crisis management approach to one based on risk and adaptive management. Flood and droughts must be addressed with the structural and also non-structural measures, and it's also important to recover the connection between rivers and floodplains. More details on the issue can be found in WFEO publication Best Practice on Droughts and Flood Management Engineering Contributions. The last measure addressed, and those are those related to sea level rise. Given that sea level will continue to rise regardless of the mitigation measures undertaken, adaptation seems to be a priority. It should be noted that 10% of the world's population lives between 1 and 10 meters above sea level. If we focus on small island development states, it should be noted that in addition to facing reaching sea levels, they are also suffer from water insecurity that will increase in the short term. Therefore, an international collaboration to address climate change in these sites is essential. We cannot forget that climate change must be a shared change. Adaptive response can be categorized into four groups: coastal protections, advance, adaptation, and retreat. Usually these measures occur in combination with each other at the same coastal location over time. Coastal protection measures may be cost-effective for cities, but not affordable for rural areas or poor areas. These adaptation measures bring multiple benefits, but we must build infrastructures from a different perspective, putting more value on the relationships with the rest of the stakeholders, such as the environment. Therefore, the design step is fundamental. We must design resilient and non-rigid infrastructures, identifying vulnerable areas and testing our proposals for adaptation to climate stress tests. The circular economy of water is important, but it's also relevant to consider the life cycle of the material we use. Defining at the design stage the dismantling of the facilities at the end of their lifespan and their possible subsequent use or recycle. We are also committed to carbon neutrality, so we need to incorporate new solutions to transform the development model. Thank you very much, José. And here you see the last publications of the WFEO Water Committee that you can check them on our website. Thank you very much, José, and the floor is yours.
Thank you very much, Ignacio, for your brilliant mise-en-scène. Is a very nice introduction for our side event. Now I will give the floor to Dr. João Paulo Lobo-Ferreira. João Paulo is Principal Research Officer at the National Laboratório of Civil Engineering in Lisbon, in Portugal. João Paulo, the floor is yours, please.
Thank you very much, President José Vieira and Ignacio. It's a pleasure and an honor to be here sharing our expertise in groundwater in new water management plans and bringing you a good news that science is targeting precisely to address those problems that we have just heard from you both before. I'm trying to say what is going on in Europe, and you will see that we are coping also with the changing pattern of the precipitation, so climate variability, etc. And what I'm going to tell you is available in a paper that was published in spring, and I've just published you this type of link here so that you are able to do this stuff. Of course, in Europe, we are having, like we are doing here, also cooperation around the world. And I'm just sharing you the 6th World Forum that was in Marseille. And we had a Shiny Europe Water platform looking to the future, scientific-based solutions for water resources management. So a lot is being done around the Europe, all the member states. You are seeing here the member states, and I will try to address this part here of the Iberian Peninsula. And this river here is the Tagus River, or Tejo, or Tajo in Spanish, and Portuguese Tejo, in English Tago, and it's 1,000 kilometers long, but not just the river basins, but also that we are sharing here for Portugal, several of our regions, the several rivers, some Portuguese only, the others sharing with Spain, but also groundwater. So a lot of what I'm going to tell you today is related to related water resources up in the, well, open sky, precipitation on the ground, surface water, and also infiltrated groundwater. All that makes our groundwater circle. So we have like 2/3 of our country's fracture media, but we have 1/3 with large aquifers. This is the largest aquifer in Iberian Peninsula, like 80,000 square kilometers in the Tagus left base of the river. And from the year 2000, we have published in Europe the Water Framework Directive. Is the Directive 60 from 2000 that was translated in the legislations of the member states. So in Portugal, it was 2005. And we have addressed in the National Civil Engineering Laboratory, where I've been working for the last, let's say, as a student also 50 years, or like a couple of decades. And then we have published those type of assessments for planning. You see here is the region of the Tagus, Ribeiras do Oeste, is financed by European Union. And what is interesting is that we have a role, a protocol, that's the guidance document 18, that says for all these water bodies, surface and groundwater, we are targeting to have what the assessment, but also conclusions and rehabilitation. Our target is by 2027 to have all groundwater, surface waters in a good status, quantitative and qualitative. But I've done my PhD in Berlin, so I'm a mathematical modeler. And you see here a watershed. And of course, you see precipitation, you see groundwater overflow, runoff. And what is occurring these days is the precipitation pattern is changing. You have much more concentrated precipitations causing floods and less groundwater recharge. And so the availability of water probably is the same. The water will not go to another planet, it will stay on planet Earth. So planning is a fundamental issue so that we can do a good job by the 2027 and later. So what is this guidance document saying? We're going to assess all the water bodies from the chemical status, like here groundwater, or the quantitative, where, as we have seen by Ignacio a little later, you are going to test also saline intrusion. And then you're going to say if this for this water body is in good status of quality or not. So if one of these tests is not good, water for consumption, global quality, water balance, if the groundwater is declining, then this water body, surface or groundwater, is not in a good state. And we have to do something to overcome this. This was the target of those plans. Of course, we are doing that by data structure models that we have here, and we address this in different types of issues. For instance, related to that Tagus watershed, we had like 1,500 wells where we have reached in depth, so in 3D, so surface and in depth, what is going on. And then you have some areas in reds where you have a decrease of the groundwater table more than 100 millimeters, and then we have to do something to see why is this happening. You see here, for instance, in different piezometrics, what's happening, and then by the measure you say, if it's more than 3 centimeters per year, then you are not able to just keep business as usual, you have to do something. Of course, we are doing this, as I was saying to you, not only on the surface, 2D, but also in depth. So in each one of these aquifers, aquitars, you are going to assess where I'm measuring. Is on this large aquifer here, is in a top aquifer, trying to see what is happening there in this groundwater body. Of course, we have several legislations like the Directive of Groundwaters, Dangerous Substance, and this Water Framework Directive and the Portuguese Law of Water. Every country has one of this law. What we are seeing here, as I was saying before, is that the wet years in blue and the dry years in red seems to be increasing in regional dimension. So something is happening, and we have to address also this. You see here groundwater scenarios that was Ignacio was showing us. We went further, and we seeing by 2071, 2100, what is going to happen according to groundwater recharge, decrease or increase due to the precipitation events. And really the precipitation pattern is very crucial because it's raining heavily. The amount of water could be the same in the average in the year, but of course it will cause floods and not so much groundwater recharge. So the precipitation pattern says us, for instance, as I was telling you here, 2071, 2100, this aquifer, Torres Vedras, is in blue. It means that we're going to lose about half of the percentage of the natural groundwater recharge. So we have to do artificial or managed aquifer recharge when we have extra amounts of water caused by the floods like the Australians, the Americans, Israel is doing, because the groundwater depending ecosystems will be affected. Groundwater level will decrease if we don't do that. We have seen empty lakes totally empty in Austria, that it's a wet country. But also we have to target the groundwater qualitative assessment. So the quantity of the pollutants inside, because we would like to supply water in good status. So for instance, in these alluviões do Tejo, this 8,000 square meter large aquifer, 1,000 meters depth in some areas, we have nitrates, we have ammonia, you have pesticides, and we are trying to see why. Why is this happening? Is this agriculture? Is this a garbage field there? So we have developed projects, sponsor, here also cooperation, EU, China, and where we have targeting, putting our devices to see in depth what is going on the surface on the real field, not in the lab, on the field, where mice, for instance, is going up at to 2 meters high, and you're seeing what the farmers are putting here. And so if in excess, it will not be useful for the plants and you pollute the groundwater. And with the mathematical models, we are targeting by the, eventually when the water comes here by diffuse flow, groundwater flow, diffuse solution, to reach, for instance, in nitrates, 50 milligrams per liter in the surface water. Groundwater, agriculture, infiltration, go to. So we are willing to have all the status. So finalizing what I'm saying, we have tried to make also different types of model, infiltration facility index, all this is in the net. So this Vieira and Lobo-Ferreira, the others one is available in the net, where you can see where you have to point out more strictly where the risk is high, like road pollution, like a car incidents going on, but also the groundwater vulnerability to saline intrusion. And I have developed with a professor of Goa University, LNEC with Goa University, method that is coming virus all around the world is using this, from Japan, Iran, Brazil, United States, Portugal, Spain, a lot of countries using this, trying to see if the water goes up in the seas, what are the aquifers that will be most jeopardized. And this is a region in the north of Portugal, Aveiro, where we are starting using a see to impress problem, addressing precisely from the scientific viewpoint what we are doing and what Ignacio was saying before, that it's our concerns. Groundwater monitoring, so groundwater recharge assessment, and trying to see if we have a landfill, if you have a mine, coal mine, if you dump the issues there, eventually it's going to reach a groundwater pumping zone. Concluding, the Tagus River Basin, as an example, was saying by 2015, those reports was from 2012, those aquifers will be, we have to do this and that, 21, and latest by 2027, all these groundwater bodies. We have basic measures, what to do, and related with the regional director of agriculture for Alentejo, Algarve, Minho, whatever. So this is the contribution from science, scientific laboratories like LNEC, universities, and as I told you, this all is available in that paper here that's available, and I think it's going. So, obrigado, thank you, Chee, merci.
Okay, thank you very much, João Paulo, for your very interesting presentation, and showing that engineers, not only scientists, engineers can really do something to face this increasing pressure of on this we call hidden treasure that is groundwater. Thank you very much for your presentation. Now I will give the floor to Professor Innocent Nhapi. The Professor Innocent is from the Federation of Africa Engineering Organizations, Water Sector Committee. Please, Dr. Innocenti, the floor is yours.
You can share the presentation?
Yes, we are now sharing your presentation.
All right, but I'm not seeing the presentation, but Let's go to the second slide. A presentation is on what we are doing in Africa in terms of managing water and wastewater treatment systems. So I'm basically reporting on what we have covered so far. And to begin with, you are familiar that in Africa we have a number of challenges, and we have identified these challenges and find our aspirations with a target date of 2063 and our Agenda 2063 agenda, which also coincided with the development of the Sustainable Development Goals. But for us to achieve these things, we need to overcome a number of challenges. Let's go to the next slide. Slide number 3. You find that for us to achieve this aspiration that we have defined for ourselves, we need to do a lot in engineering, because engineering contributes to all these efforts. And
can you change the slide, please? Theo or Ivan, be aware that we must have changing the slides.
You are changing the slides, huh? We're on slide number 3.
Number 3.
Yeah.
Please do so.
Okay. So on that slide number 3, it just shows some of the numbers, the deficits that we have in terms of engineering contribution, and this shows the potential of what we can do if we put effort into developing capacity. Next slide, you will see that a number of challenges have been defined in engineering, which are to do with the skills gaps and capacity in STEM, the training itself, the deficit in training, and that the issue in Africa is not about just numbers. Numbers are lacking, but also the issue of quality is lacking. So we need sufficient skills there. And there's also an emphasis on the relevance of our programs to problem solving, especially solving local problems, because our problems might not be the same as what we get in other continents. So we need to develop those skills. And the question is, do we have the capacity, and what do we need to do to enhance capacity to achieve this? We go to next slide. So in terms of responding, you to see that we need to respond in a number of areas under engineering, but looking at the situation from 2020, where we had serious problems with cyclones, serious problems with COVID-19, it was decided that we focus initially on the water sector and come out with a strategy that can be upscaled to other engineering sectors like energy, mining, and manufacturing, all these other areas. So it was decided that if we are going to do this, we will be targeting training people who are already doing their job, and then enhance their skills and competencies so that they can do their jobs better and increase their productivity. So action-based learning was chosen because it has a number of advantages, where we have management teams and we train the management teams working as teams, so that this training is not focused on achieving certificates, but is focused on competencies and improving competencies. So our primary aim there was to close the gap by creating critical mass of competent and committed engineering leaders at all levels who are able to deliver performance improvements in their engineering-based organizations. Next slide. You find that this course that we developed, which was targeting water and wastewater treatment plans, was trying to address a number of issues that these plans, which are to do with the knowledge itself of the systems, then daily operations, and what a manager is supposed to do and what other workers are supposed to do as a team. So the training was face-to-face, it was hybrid, face-to-face and online. I'll talk about challenges later. And we settled on 5 days, concentrating on technical issues and then also concentrating on management issues. Because what we realize is some engineers might be very good as engineers in terms of their skill, but in terms of management, they will be lacking. Then also in terms of managing that infrastructure, there are certain things that come in between the technical and managerial issues that are the people who are running these things are supposed to be conversant with. It also involved field visits. These field visits, you do notice that these are people who are already working, so they know the plans. But the field visits, they focused on a tool, because these people, they developed a tool which they applied in the field to assess the treatment plans. And then they will present this in group presentations. This was one variation. The other variation is they looked at their treatment plan as a team, and then they looked at the challenges, then they develop a performance. They'll be coached on how to do it. And then from there, they also had their written assignments. And these written assignments, they focused again on the performance improvement plan and the performance and the personal development plans, where they would look at themselves and the competencies that are required by their organizations, and then they do self-assessment and look at how they are going to develop those competencies that are required by their bosses. The courses were the course evaluation, and they received the certificate of competence against the certificate of attendance, because here they will be examined, and if they did not do well, we had to redo the exercise until they understand what they are supposed to do. Next slide. Next slide is just on the assessment that I've already talked about. But I want to go to the challenges that we faced. You can see that even in my presentation, I faced some challenges in terms of virtual delivery mode. The network connectivity in Africa is still a challenge. It's desirable, but still a challenge. Then also the level of participants and commitment on online courses, it was not as what we wanted, because online you'd find that sometimes people leave. You are always checking on the numbers. Sometimes you've 10, sometimes you've 15, sometimes you've the maximum number. The participant selection also, we wanted to emphasize on the teams. That's the most important thing in the action-based learning, so that they work together, they identify the problems, they brainstorm together, they find solutions together. So it's an experiential learning process, which is best done as teams. And sometimes finding the teams when you have problems with the capacity, where the organization don't have sufficient manpower, is also a challenge. Then dealing with several levels of understanding can also be a challenge, because if you notice, we are dealing with engineers, technologists, technicians, artisans, up to, so you would find that the understanding there becomes a bit challenging, and you need to attend to the different levels in their understanding. The field visits, the field visit became very difficult now for online to attend the field visits, but this is an important aspect of the learning process. The funding also is a challenge, maybe, which we can work together to address. In my
Well, I'm afraid that we have lost the connection with Professor Innocent Nhapi. Ivan, yes? Ivan?
Yes.
Do you have... we lost Professor Innocent.
Yes, please, Mr. Nhapi can disconnect and reconnect.
Okay. But I think that Professor Nhapi was finishing his presentation as well. Maybe we can consider that he's finished, and I thank Professor Innocent Nhapi to bring to our webinar this most important issue about the lack of skilled engineers for sustainable development, mainly in the sub-Saharan region of Africa. Okay, thank you very much. So I will continue with this webinar, giving the floor to Dr. Qian Yu. Dr. Qian Yu is a senior engineer at the China Institute of Water Resources and Hydropower Research. Please, Dr. Qian Yu, the floor is yours.
Thank you, President. And I will share my screen again. Can you see it?
Yes.
Yes, okay. Okay. And hi, everyone. Good morning, good afternoon, and good evening, and depending on where you are now. And this is Qian Yu from China Institute of Water Resources and Hydropower Research, IWHR. And it is my honor to give a talk at this STI Forum. Today, my topic is about adapting to climate change, engineering support water security. And my report will include these 4 parts. So let's go to the first part, is the water challenges that we are facing right now in China. Okay, as you may know that, and you can see that nowadays in China, we are facing 4 major water challenges. They are water scarcity, water hazards, water pollution, and water ecosystem degradation. So for the water scarcity, such as water supply disruptions, drying up of river channels, and for the water hazards, such as the river basin flooding, urban flooding, and flash floods. I know all of these problems seems and sounds very traditional, and I think most of the countries in the world also face the similar problems. However, the climate change just make these problems more complex and more uncertain. And here I just show you some figures here, which is from the latest report published by IPCC. And you can find that the surface temperature just rise. And with the rise of the surface temperature, the annual wettest day precipitation is projected to increase in almost all continental regions. So here I also show you some evidence for the global climate risks, especially on water scarcity and flood risks. So the climate change just make the extreme heat and heavy rainfalls more frequent and more intense. Also, the droughts in some regions also increase. So our question is how to reduce the climate risks. Yes, the answer is adaptation and mitigation. But my topic today will mainly focus on adaptation. So our next question is, how has China adapted to climate change through water engineering solutions? And I will give you some solutions and cases in China. Before that, I want to show you the China's water governance philosophy. You know, through the hard works of the decades, that China's government has done many efforts to achieve the sustainable development. And we just put forward a new development concept. It includes 5 parts: innovation, coordination, green, openness, and shared benefits. And when it comes to the water governance, the fundamental principles including 4 parts. The first is prioritizing water saving, and second is balancing water allocation, and third is the systematic water management, and then last is harnessing both public and private forces. And through these works, we just make a very significant progress to achieve the sustainable development goals, especially to achieve the SDG 6 and SDG 11. Okay, here I just show you 3 engineering solutions and to show you how we just enhance our overall capacity to ensure the water security. Okay, the first case is raise water use efficiency to improve the efficiency of water resource utilization. And second case is a build national water grid to strengthen the water resource allocation optimization. And the last case is improve the flood control system in the river basin to enhance the water disaster prevention and control capability. So you can find the first 2 cases just to show you how we solve the water scarcity. And the last case just to show you how we solve the water hazards. So, okay, the first case, raise the water use efficiency. As you may know that the spatial and temporal water and soil resources in China are mismatched. So the irrigation plays an important role in food production. So after a hard work of the decades, we just developed cutting-edge technologies and equipment like the precision drip irrigation, variable rate sprinkler irrigation, and smart irrigation. Also, we improved the water and fertilizer management and controlled irrigation in paddy fields. As a result, the irrigation ratio of the arable land in China is around 51%, and that's about 2.5 times higher than the global average. And to better allocate the water resources, as you may know that the water resources in the south of China are abundant. However, on the contrary, in the south, in the north, the water resources is shortage. So the China's government just put forward a very huge project called National Water Grid. And you can see the right figure. It is composed of 4 horizontal lines, and they are Haihe River, Yellow River, Huaihe River, and Yangtze River. Also, we constructed 3 south to north water diversion projects and transferred the water from the south to north. And until now, that eastern route and middle route has been established. So through these methods and these measures, these projects, we just improve the total water supplying capacity significantly. And you can see that in 2021, the total water supply capacity is around 890 billion cubic meters. And in view of the limited time, I just show you 2 cases to address the water scarcity. In fact, in China, that we take integrated measures. Besides increase the water use efficiency and increase the water supply capacity, we also cap the total water use, and we also develop the intelligent, smart water management systems. So as a result, we feeds the 20% of the world population and contributes 8% of the world GDP, with only 6% of the fresh water and 9% of the arable land. You can find we make a lot of efforts to achieve the SDG 6. Well, for the second challenge is water hazards, that we mainly focus on enhancing the preparedness through engineering systems and non-engineering systems. And among the engineering systems, we just established the reservoirs, levees, flood storage, detention areas, gates, and locks. And until now, that we have constructed more than 300,000 kilometers of the river embankments. And we have established a total of more than 98 reservoirs, providing a total storage capacity of about 900 billion cubic meters. Also, we established 98 national flood storage and detention areas. And for the non-engineering measures, you can see here the first important key part is the monitoring, early warning, and forecast. And this video just to show you how we use the big data, BIM, IoT, this advanced technology to develop the digital twin for the Huaihe River. And you know, it's tremendously useful for the flood control for the whole river basin. And second important key part is the risk mapping and zoning. You see, we just do many works to accelerate the computing velocity using the heterogeneous method, combining CPU and GPU. Also, we just public the flood risk to the stakeholders and help them to do the land use planning. And the results are very significant. Here, I just show you two figures. The first figure is the dead person or the missing person. And the second figure is a percentage of the flood-induced direct economic losses. And you can see both figures just drop to the bottom. So that means we did and we achieved a lot of efforts to achieve SDG 11. Well, let's see. The last part is international solidarity. You see, among the 17 SDG targets, the last one is partnership for the goals. It's the last but not least. And you know, IWHR is the largest research institute in China in water resources and hydropower, that we host global secretariats or national committees of 10 international organizations. Also, we do the water educations for the children in Asia and in Africa. And we also help to build the clean water projects in rural areas in Southeast of Asia. So in conclusion, we believe that engineering solutions are very important to achieve the water-related SDG target. We also believe that we need to create a stronger solidarity in achieving SDGs, and that will deliver good for all. And that's all my presentation. Thank you. Thank you, President.
Okay, thank you very much, Dr. Qian Yu, and congratulations for this comprehensive and very interesting presentation on engineering solutions for water resources management in China. Thank you very much. Now we proceed this event with the presentation of engineer Martin Manuhwa. Martin is the chair of our WFEO committee in engineering capacity building. Martin, the floor is yours, please.
Thank you, Mr. President. My on what we can do using technology, especially in Africa, to deal with the water shortage. What we've done is like a member of our committee, we have run a course in South Africa, in Zimbabwe and Namibia, where we are dealing with the infrastructure, municipalities, and capital issues that they face. To emphasize to achieve the Africa we want and accelerate the delivery of the goals, we need to work in partnerships as well as apply technology in the field of water. And you know, without engineering, the world is going nowhere. As engineering provides solutions to mankind problems. So for us to achieve the 2030 agenda for peace, people, planet, and progress and prosperity, we need to apply engineering technologies. And as such, our committee was looking into we can train and partner with colleagues. I would like to acknowledge Ignacio, acknowledge the Department of Science and Innovation, acknowledge WFEO and FEO for putting together such a that we started with the pilot of the 3 countries, but we are going to, Mr. President, you did touch on when you introduced the session, and most of which to make sure the Internet of Things, to ensure there are sensors around water preservation, water solutions, such sensor the irrigation by measuring the humidity, temperature, and many other parameters using even big data analytics. So what we're doing together with CSIR South Africa and reached out to the Water Committee and WFEO to ensure that we enlarge how we can use the digital transformation of the water delivery. We're going now to use technology that is already set, and I think I will give a few graphics of what can be done in the 4th Industrial Revolution. And these technologies have been so disruptive to the extent that if the world unites and works together, we can solve some of the basic problems that our people have on water adaptation, delivery, distribution, and many other things to deal with climate change. Again, disruptive technologies will assist us to make innovations around building that capacity in our engineers. These technologies, they change the way we do things. Our forefathers, for instance, did not leave the Stone Age because they ran out of stone, or Iron Age because they ran out of iron. They found better, innovative ways of doing things, and we are going to follow. So we need the new knowledge. We need that ability to develop and capacity, this willingness to accept new forms of technology, marketing, sales, and also we need businesses to be more responsible, especially with artificial intelligence. Hence, our WFEO saw it fit to create the capacity building committee. Again, we are motivated by this paradigm shift of disruption, where we are looking at the digital future spurred by globalization, community living, as well as rising entrepreneurship. We are now from the first, second, third, and fourth. We are on the 4th industrial. The first 2 revolutions were to do with efficiency, doing things more mechanical ecosystems. But the 3rd was more to do with doing the right thing. Digital automated systems in water, we've now seen some great impact using a lot of these environments around Internet of Things, Internet of Services, Internet of People, that have now delivered smart water, smart grids, smart mobility, and smart businesses. With these pillars and these technologies, which the president of WFEO spoke, we are now applying them in research by practitioners in the municipality, for example, using satellite to measure the quality of water, turbidity, a lot of other systems that we have looked into this. And we have created a framework which then needs everyone to work together: industry, governments, professional bodies, the United Nations, the other Africa Union, and many people. to ensure that we can look at the key challenges. We will be ransomed. We also data scientists, more engineers, and this transformation needs for us to change all our skill sets, our policies, and our culture. We're then going to look at the technical development WFEO, higher institutions, education, our governments have to craft us. Is one, we are two, infrastructure maintenance must be automated. And three, we need an environment for data and Industry 4.0. Is supporting and regulating these policies. Done in the, we have more people to join engineering, especially women, so that we can together look at how we can deliver solutions. This where we feel water, seas for government, Sauga, we teamed up with all these teams to come up with a model of this training. And we did our benchmark with the Germany Water 4.0, where they have looked at creating with through big data analytics, through many other things, leakage detection, and so many things that we are looking at and training our people. Again, this application of Internet of Things is so exciting for us. And we have more research papers. Mr. President, when you come to the Africa Engineering Week in South Africa, we will showcase some of the outcomes of this. So we need to be doing water quality control on water reserves, efficient systemic water management, water leakage detection, water quality and safety monitoring, transparency of consumption, as well as maintenance of the infrastructure. Just in short, you can see the matrix there that looks at how many things we need to do and what IoT technologies we need to deploy. Because of the limited time, I will not go into details, but just to recommend that we should commit further development of capacity to increase the number and quality of engineers, technologists, and technicians to meet these standards that we require. And after our pilots, we are so convinced that we can now deploy this training throughout Africa, South America, and other regions. And I'm happy Qian Yu has asked for partnership. And of course, we have already partnered SADC, the South African government, many universities here to expand and explore and share knowledges. We then also commit further to ensure that we have, we move and take Africa, especially Africa, because of the dedication to this UN STI Forum, to the next level of digital expansion and also solutions to our water program. Mr. President, I thank the organizers, Ignacio, yourself, and the UN for this opportunity to give a small snippet of our project under the capacity building of your WFEO as the president. And in Africa, we always say, if you want to go fast, go alone. If we want to go far, let us go together. I thank you. Thank you very much. These are our partners in the project that we are doing under the WFEO capacity building and FEO capacity building DSI project. I thank you.
Okay, thank you very much, Martin, and congratulations for your presentation that once again, you highlight the very crucial issue about having well-trained engineers for Africa. That is a key factor for the development of this continent and these regions. Thank you very much, Martin. Now, I will proceed giving the floor to Dr. Chee Meng. Dr. Chee Meng is the Chief Engineering and Technology Officer at PUB, Public Utilities Board, Singapore's National Water and Coastal Protection Agency. Dr. Peng Chee Meng, the floor is yours, please.
Thanks, Mr. President. Maybe I would like to start off the presentation first by thanking the organizers, President Vieira, as well as Ignacio for giving me the chance to speak at this important event. I would like to first start off by introducing briefly about Singapore and the water context that we operate in. So Singapore is a small island within the Southeast Asian region, and we have a small land area of about 700 square kilometers. We have a lot of rain, about 2.2 meters worth of rain, but the natural problem is that we do not have sufficient land to store all the water that falls onto our small island. So naturally, we are a water-stressed country, but over the years, we have built up some capability to overcome some of these water stress challenges. In terms of where my organization is
Dr.
from,
Peng Chee Meng, maybe you can put in the presentation format your screen.
Oh, hold on for a while.
Below yeah. You see? Okay, nevertheless, please continue, please.
Oh, okay, hold on for a while. Maybe I just use this. Yeah. Yep. So over the years, we have built up 4 diversified supply sources of water that help us overcome some of our water challenges. The first source of water comes from from the water catchment. We have converted about 66% of our land area to water catchment areas. And these waters that's falling onto these catchment areas will flow into one of our 17 water reservoirs. In this photo that you see below, the Marina reservoir that indicates that is shown there is actually an urban reservoir, meaning that the water falls onto the city that you see in the background and flows into this particular reservoir. So we are trying to maximize the water catchment within our small land area to capture as much rainwater as possible. The second source of water naturally is from Johor, Malaysia. So this is an important source of water that we continue to import today from our neighboring country. The third source of water that we have is new water, and that is really a high-grade recycled water that we produce by collecting and treating our wastewater from throughout the island and producing a high-grade recycled water through advanced membrane technology. The last source of water clearly is seawater desalination. And this is, and in this particular case, we produce desalinated water using membrane technology. And one of the latest plants that we have employs dual mode membrane technology, whereby we either tap seawater or fresh water, depending on the tides, to lower the energy costs of seawater desalination. But notwithstanding having addressed some of these water challenges, we feel that there's a looming crisis, which is climate change. So it has particular impact on Singapore because the main problem is that climate change exacerbates the extremes. On one hand, we are projecting a 25% increase in rainfall intensity, but at the same time, we also face an increased risk of prolonged droughts. In terms of temperature, we are foreseeing a 1.4 to 4.6 degrees increase in mean daily temperature. And these, of course, have a corresponding impact on the water demand by households, as well as industry, which we project to increase with increasing economic development. In terms of sea level rise, we see a 1 meter rise in mean sea level by year 2000, but that is mean. If you take into account extreme events such as high tides and storm surges, the increase in sea levels can be up to 4 to 5 meters high. So what this means is that we have to prepare for a future whereby it is more uncertain, and we need a lot more resilience into our water system. I would like to chart maybe 3 new priorities that we have for our organization. We are seeing that we need to ensure sustainability, circularity, as well as resilience in the face of change. And we are planning and implementing a number of innovative and adaptive technologies, strategies to be able to overcome some of these challenges. In terms of sustainability, we are charting, we hope to move towards a system whereby we are decarbonized, such that we are achieving net zero carbon emissions in our operations. In terms of resilience, a large focus will be on coastal protection. And in terms of circularity, we hope to achieve some amount of resource recovery so that we will be sending zero waste to our landfills. I will talk about briefly on on some of these initiatives that I have. First, on sustainability and decarbonization, we have a plan to peak our carbon emissions by 2025, and in the longer run to achieve net zero carbon by 2045. We hope to achieve this by a 3R strategy, incorporating the replacement of carbon-emitting energy sources with renewable energy to reduce our energy consumption, and thereby reducing our carbon emissions through having more energy-efficient water and wastewater treatment processes, as well as reducing the energy required for sewer desalination. In terms of removing carbon, this is to really remove carbon from the environment so that we can abate some of our carbon emissions that is hard to remove through other means. This will require us to perhaps sequester carbon from the environment so as to gain some form of carbon credits. An example of such a decarbonization or removing carbon from the environment type of perspective comes from the use of alkaline electrolysis technology. In this case, we are running a large number of desalination plants, and we also know that the ocean is a large sink for carbon dioxide. If we can incorporate this alkaline electrolysis technology ahead of our desalination plant, we will be able to sequester carbon dioxide from the ocean and produce solid carbonates. And this would in turn allow us to achieve some form of carbon abatement. At the same time, the seawater will also be softened since it's depleted of calcium and magnesium, and this will allow us to desalinate the water in a more efficient manner. So we have ongoing pilot trials to test this technology, and we hope, if overall is successful, we hope to scale it up in the year 2026. In terms of resilience, we have a three-point approach to coastal protection. First, we hope to rely on a holistic risk assessment whereby we will use science-based approaches to try to forecast storm surge events. In terms of flexibility and adaptive design, what this means is that we are building our coastal protection measures incrementally over time, and they will hence have to be adaptive and flexible to cater to the uncertainties of current climate projections. In terms of integrated planning, we are talking about multifunctional use, whereby our coastal protection infrastructure can be dovetailed with other land users. An example of this is to use Xbox Plus. Xbox Plus is a type of a Lego type of a cube that is used in the Astrodiet in the Netherlands, whereby it is a major dam to protect against dam from the sea. So this X block will stack up one on one like Lego, such that they will form a contiguous layer of coastal protection defenses along our sea coast. Some of the possible deployment designs are shown in this particular slide. So lastly, on circularity, our aim is to really achieve zero landfill to waste. Currently, we are contributing about 6% to landfill after incineration of our wastewater sludge. This is obviously not sustainable because the landfill is the only landfill left in Singapore, and we have a longer-term plan to try to achieve zero landfill. We again hope to do this through two methods. One is to reduce sludge coming from our waterworks, and we do this by replacing our conventional alarm with some ferric chloride type of a coagulant. Secondly, we have to also deal with the wastewater sludge itself. The sludge after anaerobic digestion, we would subject it to further gasification to convert it to slag. Slag is some form of a gas crystalline particles that is able to incorporate many of the contaminants from from sludge, such that it is able to be put into beneficial use, such as landfills and roadworks. Obviously, we cannot, some of these technologies are pretty difficult to achieve on our own, and we work with multiple partners. And one of the ways that we encourage collaboration is through the Singapore International Water Week Forum, whereby we have a number of events that is scheduled to take place in June next year. One way, so currently the call for nominations for the Liquid Water Prize is open, and you can scan the QR code there for some additional information. At the same time, the Water Convention, which is a conference, is also open for papers in 26th of April. With that, I thank the organizers for my chance to speak at this important forum. Oh, am I totally lost?
José, your micro is off.
Yes, I'm sorry. Thank you very much, Dr. Pangshe, and your presentation with the very interesting advances in controlling these climate change impacts in Singapore. Thank you very much. Well, dear colleagues, dear participants, we are now out of our time, but I think that we have maybe more 13 minutes for having the floor for and room for some questions. And I ask Ignacio if you are ready to have one question for each of our speakers to use this now 12 minutes to have a little bit more insight from our participants, and to give the floor to our speakers to explain some of maybe not well understood presentations. Okay.
Well, we have several questions from different people. And the first question I think it's for Dr. Lobo-Ferreira, is if the artificial managed recharge is a success solution that can be extrapolated to all sites or countries. And can you share any good examples of good practice that we can look at?
Yes, as a matter of fact, that's a good question, and I was trying to have this type of answer also put here. I'm trying to share my screen precisely on this issue that we are having here. For instance, in southern part of Portugal, where we have tried different types of approaches for large wells, for riverbeds, where you take the roots, and then we have assessed in a project that is MARSOL, demonstrating managed aquifer recharge as a solution to water scarcity and drought. We have used this in the southern part of Portugal, besides in Spain, Catalonia, Llobregat, Israel, Greece, etc. All this is available really in the net. If you go to www.marsol.eu, the mathematical modeling that we had there, and that's also another question in the chat, the Excel files there about mathematical models. We have precisely a white book on mathematical modeling for for managed aquifer recharge, like this one. So really, we are trying to interconnect to different parts of the world, like China, and also the Portuguese-speaking countries, like Angola, Mozambique, Cape Verde, Brazil, where we have addressed this. If you use through Ignacio or the WFO, I can manage to have this type of solution. Yes, for us is a sound, safe, and sustainable technology, and we have used trying to see how much can we use not only for storing the water, but also like in the southern part of Portugal to clean this water to nitrates. And we had a PhD that we have made there, and 20 cubic hectometers could reduce the nitrate pollution to the legal values of 50 grams per liter. But what we were targeting in this area here is to use the overland, the flood years, like in 2005, we had large rains in the southern part of Portugal, in Algarve, about 52 cubic hectometers. And if we have used this aquifer where we have done a lot of research, where to plug in, we have different types of models to see what is the best location to place your facilities, different types of facilities. Then 4 years later, we had a large drought where we have overpumped, creating saltwater intrusion in this area here in the progress and outflow. And yes, managed aquifer recharge for us is a good, sound and sustaining technology. In December last year, the Portuguese Parliament was making like a suggestion to our government, do implement here. Of course, you have to have the quality issue, not to jeopardize through the injected water, the quality of the groundwater. This is a must to avoid further pollution, but it's a good example and we are able to do that. On the other question that was about the Tagus River Basin Management Plans, we are using different types of model that's available worldwide, like the BALSEC, precipitation, runoff, groundwater recharge, using the mod flow. And we, of course, we are doing a lot of cooperation and we are able to do that further.
Okay, thank you very much, João Paulo. The next question is for Professor Innocent Nhapi. Do you hear us, Innocent?
Yeah, sure.
They ask regarding capacity building needs in Africa, in water, in which field is more necessary? Design phase, construction, or operation?
Design phase, construction, or operation. I think at present, I would say operation. Why am I saying operation? It is because we have a lot of infrastructure. It doesn't make sense to continue constructing more infrastructure when the existing one is deteriorating. So we have serious problem of deterioration of infrastructure. That's why in our pilot we focused on the operation and maintenance so that we preserve what is there. Then we can keep on extending the infrastructure. We have had a lot of decades on water and sanitation, but if you look at what have we achieved from those decades, you find that what we constructed during those years has deteriorated because of lack of maintenance. And the spirit of maintenance, unfortunately, in the African context is always lacking. In most African languages, you don't have a word on maintenance. Thank you.
Okay, thank you very much, Professor Nhapi. The next question is for Dr. Qian Yu. Do the water transfers you saw have environmental problems? Or how you saw? I guess that they asking how you saw.
Okay, actually, I did environmental risk assessment of the South to North water project, and you can see that the environmental risk is very limited. And compared to the environmental problems, the water transfer project indeed provide a significant ecological impacts on the North rivers and the groundwaters, and in that were. It just improve the groundwater level, and it provides the ecological base flow to the rivers. As you know, maybe in North China, that many rivers has no rivers, no waters. So this water from the south can provide them to the fish species and other animals and water animals. That's it.
Okay, thank you very much, Qian Yu. We have 3 more questions. The next one is for Martin Manuhwa. What are the difficulties you are facing to implement this disruptive revolution in Africa? I don't know if Martin is there. If not,
yes.
Yes, okay.
It's the difficulties are quite many, but I highlight on the major one. I think the major one will be the financing of the projects that we want to do, especially the capacity building projects. The second one will be on the acceptance of the solutions that we are proffering. So this, I think, among many challenges I might not have highlighted, the buy-in from the policymakers, from the international bodies, and also participation with apathy by our own professional bodies in mentoring young engineers, and a lot of things in the engineering value chain. So what we are doing is we are going to come up with a conceptual study to point out all these challenges and identify the solutions on how we can then work together with other continents like Europe, China, and Asia, to come up with multidisciplinary teams to ensure that we do our engineering studies, we offer the solutions, and then we also build the capacity. I'm not sure whether I captured the question correctly, but some of the difficulties that we are facing.
Thank you very much, Martin, for your answer. The next question is for Dr. Pang. How you solve the problems of brine of the desalination plants?
All right, thanks for the question. So essentially, for the issue of brine, that is a known problem. So we have first carried out an environmental impact assessment, which will first guide us to see whether there are sensitive receptors of organisms within the area of the desalination plant. And then as part of this process, we also identify areas of the sea whereby the currents are high. And then we will typically extend a long outfall into the sea, into these high current regions to more evenly disperse the flume of the seawater desalination brine. So these outfalls can be long, and they can be quite costly to construct. But it also here just lies just shows our commitment towards minimizing the impact of brine on the aquatic life. In addition to all these engineering structural measures in place, we also have a long-term monitoring whereby we continue to see whether there's any impact on the marine life in the vicinity of our plants. Yeah.
Thank you very much, Chee Meng. And the last question, I think it's for Lobo-Ferreira, Professor Lobo-Ferreira. Any research on the impact on aquifers of carbon storage for injection into the underground? Or maybe it's for Dr. Pang, I don't know which one. Maybe Chee Meng, you can answer that because you
yeah, unfortunately, we do not sequester our carbon was underground. That I don't think it is. We are not sure whether that's viable. As far as I understand, if we want to sequester carbon dioxide underground, we need certain geologic structures, right, in terms of aquitard and also a confining layer and to keep carbon dioxide under pressure. For us, we are essentially sequestering carbon in terms of solid carbonates, and then those carbonates are either recycled for subsequent uses. So it is not our practice to sequester underground, unfortunately.
Okay, I don't know. Thank you very much. Okay, go ahead, João Paulo.
Yes, so indeed, we have not done that, as far as I know, in the southern part of Europe, but some areas in the Northern Europe, I think even Denmark or Scandinavian countries are trying to see how to put the carbon dioxide, trying to remove from the atmosphere and putting deep on the plates, so the shell plates, so below the groundwater and the surface, so below the crust of the 20 kilometers down there. So in Northern Europe, we are really trying to have that in a huge, trying to take from, and it's going to be industrialized from the atmosphere to plug in completely deep in the magma levels of the planet. But this is still very expensive, but it's a research going on some countries.
Thank you very much, João Paulo. Well, José, I think that we are just running out of time. So the floor is yours.
Yeah, thank you very much, Ignacio. Maybe I have just a final remark about what was our field of this webinar. Climate change and the consumption patterns of today's society have increased the pressure on all natural resources, especially water. Not only have global water demands grown exponentially in recent years, but a very high percentage of wastewater returns to ecosystems without being treated or reused, polluting our rivers, environment, and biodiversity. Droughts and floods are also increasingly perceived by society as the visible face of climate change. Faced with this situation, humanity must adapt to these new scenarios. I hope that this side event has served to highlight the importance of engineering and engineers, what they can have in resolving or at least minimizing their negative impacts, allowing for a greater sustainability, circularity, and resilience of this valuable resource. And we are now about to an end of this webinar, and I should congratulate and thank our speakers and of course the questions from our participants, and a special mention to Ignacio González-Castelao that is hosting this webinar. And for all, I was very pleased to participate in this very exciting and very interesting webinar. Thank you very much. And I hope that we can meet again in another place in another time. Thank you very much.
It was a pleasure.
Thank you very much.